we go into the periodic table of elements. Agriculture will tell us we need 17 essential nutrients for a plant to live. That's true. However, that doesn't ensure quality and nutrition. These have to be there or a plant won't function. But there's a far difference between plant function and plant nutrition. There's a reason that we have approximately 90 naturally occurring elements in this world. And it has a place in creation and a place in biological processes. So in fixation or recombining of elements, water is simply two H's, two hydrogens, and an oxygen. And it has a molecular weight of 18. Carbon dioxide is carbon and two oxygens, and it has a molecular weight of 44. Nitrogen gas is N2, has a molecular weight of 28, and oxygen gas is O2 and has a molecular weight of 32. And so in the construction of these elements, they're all insoluble, but when they're combined in different ways, they become available. So when we look at a plant's dry matter weight, carbon occupies 45%, and it comes into the plant by the way of CO2. Oxygen, 45%, CO2, hydrogen, and water, O2, become H2O. And nitrate is naturally formed from atmospheric fixation. When lightning occurs, its heat factor is 3000 Celsius. And that breaks the triple nitrogen bond between two nitrogen molecules, and the two oxygen molecules, it's a double bond. And that allows it to form into rain. And so you pick up nitrate from lightning, but it's only going to supply a small percent of the plant's material as far as the nitrogen needs. Hydrogen is 6%. Again, you get it from rain and you get it from ammonium. Plants take up nitrogen, 1%. It can come from a nitrate, can come from ammonium. So the rhizobium that you have for your legumes, whether it's alfalfa, a pea, lentils, soybeans, legumes produce, the biology is able to take nitrogen gas out of the air and fix it into ammonium for plants. And this is a brilliant process, and it requires trace elements to do this. But we all understand that microorganisms can take N2 gas from the atmosphere and fix it. In our atmosphere, it's 78% nitrogen, 21% oxygen, less than 1% argon, and then the rest is some CO2. We have 35 tons of nitrogen that sit above every acre. And that is there to harvest it if we use the intelligence to do so. Magnesium, potassium, calcium, phosphate, sulfur, they make up another 2% of the plant's dry matter weight. And that only leaves us 1/2 of 1% left. So I want you to look at this entire mineral profile. 9 elements here make up 99.5% of the plant's structure, dry matter weight. And so what are the other 1/2 of 1%? Right here, let's look at the nutrient demand for 300 bushel of corn. So in the beginning, we have nitrogen, phos, potassium is the orange, sulfur is the yellow, phosphate is the blue, and nitrogen is green. This is the diet and the amounts of NPK and sulfur that the plant needs at various times to accomplish this 300 bushel. I want to show you this in perspective of the carbon dioxide requirement for the same 300 bushel of corn. Your carbon dioxide demand is at least 30 times of your fertilizer demand of NP and K and sulfur. 30 times. Yet, because we don't see the atmospheric gases, we don't manage for those. They're almost completely oblivious. And then the next problem is because we don't see the soil microorganisms, we almost manage absence of their contribution. Yet the soil microorganisms and the atmospheric gases are up to 96% to 97.5%, depending on where you put nitrogen, of our entire plant structure. And so I want to convey how important it is that you look at all of the components that build the plant. If we don't manage for carbon, hydrogen, and oxygen, there is no possible way to increase plant mass. No possible way. In wheat at 100 bushel per acre, this is the nutrient demand of a wheat plant. In relation to the carbon dioxide, carbon, oxygen, hydrogen demand, the carbon dioxide is in blue, all of the NP, K, and S is in red. So it's a staggering amount of nutrition and structure that should not be avoided or excluded from our management processes. If we look at the tallest building in the world in Dubai, you can see the relationship of CO2 in relationship to NPK, S, calcium, magnesium, and everything else. This building is over half a mile tall, 2,800 plus feet, and the vast majority of it would be CO2 if this was a plant. 100 years ago, this gentleman actually stated, carbon dioxide is more important to high yield potential than N or any other element. And he was absolutely correct. The other half of 1% of the plant's dry matter weight are trace elements. And so obviously they're not structural. They're not contributing to the great structural amount of the plant. At 0.5%, they're too small of a ratio. However, they're critical to every function that goes on in the plant. So ionization is the process of putting things together. And carbon, oxygen become carbon dioxide. Hydrogen, oxygen become water, H2O. Hydrogen, nitrogen become NH4, ammonium, 1.5%. The rest of our minerals combined are 2 plus the trace elements at 0.5%. So fixation is simply carbon and oxygen becoming CO2. Oxygen, hydrogen becoming water, hydrogen, nitrogen becoming ammonium. So they're put together in various ways. This is 97.5% of a plant that you don't need to buy. It's there if we learn how to convert these inorganic, insoluble elements into organic forms of plant nutrition that are usable. Enzymes. Now, every organism that lives, from a microbe to an insect to an animal to a human and a plant, comes with its own enzyme package. Everything is there. And these enzymes put things together. They also take things apart. The vast majorities are proteins, and they activate the processes of change, but they don't become part of the change. And they increase the rate of these reactions by thousands to millions of times. And they're highly specific. And what that means is every enzyme has a very specific activator. So the micronutrients become the spark plug or the catalyst to start the enzymes. So I want you to think about it. I know all of you guys got tractors, and I even own one myself. You guys think I didn't farm, but you're wrong. We actually do a lot here. But the tractor does not come with a lifetime supply of fuel. You have an incredible amount of biomass. You can have a 50,000-pound tractor, and without fuel, how far does it go? Don't get any work out of it. Well, it's the same with a plant. If I don't have 50 gallons of fuel for my tractor, it doesn't do anything. If I don't have micronutrients for my plant enzymes, they're not going to function. And so when universities say we don't need trace elements, well, because they're such a minor part of the plant, they're overlooking the value of their function. The trace elements are running hundreds and hundreds and thousands of plant enzymes. And without the trace elements, the enzymes don't function. Just as a tractor without fuel, it is not going to function. So molybdenum is essential for nitrogen fixation, for nitrogen alterations, and we're going to go into that. So enzyme bonding, we can take carbon, hydrogen, oxygen, and it can become part of our RNA and DNA. It's just in how many carbons, how many hydrogens, how many oxygens are stuck together. The same three elements can become lactose or a carbohydrate. Simply more carbons, more hydrogen, more oxygens. We add a nitrogen to our carbon, hydrogen, oxygen. Now we're making amino acids. And we can go back in and make lipids through the process of just restructuring how many carbons, hydrogens, and oxygens are put together. So this is enzyme bonding. They're going to take raw materials and start building components. This is critical that the trace elements are there. And not just a few trace elements, dozens and dozens and dozens and dozens. So here's the brilliant process of photosynthesis. And this is a couple things that we are going to be able to verify where we are in our plant's functionality, is we're going to be able to measure, and we do measure chlorophyll. We also measure sugar, sucrose. So I want to go through this process of photosynthesis because photosynthesis is the most important function in our plant for yield and quality. So if we want to raise our yield, we want to double or more increase our yield, it is not going to be driven by NPK. It's going to be driven by carbon, hydrogen, and oxygen. A little nitrogen, a little phos, a little potassium are needed. But this is a case where the tail at 2 or 3% does not wag the dog at 96 or 97.5%. In photosynthesis, we're taking 6 carbon dioxide and 6 oxygen. The plant, through its intelligence receiving sunlight, creates a process of photosynthesis where we now form sugar and we have oxygen. And so I'm going to, in the next slide, we're going to map out the process of how this happens. But in the process of this, light respiration, we are creating chlorophyll, and we can measure the chlorophyll in a plant. This gives us a direct indicator of how the process of photosynthesis is working. If we have very low photosynthesis, very low chlorophyll, that means we either have a CO2 problem or a trace element problem. Remember, there is no NPK in this process. So photosynthesis breakdown, 6 carbon dioxide, 6 water, and we split those, and we now begin to form sugars and oxygen. You cannot split the water molecule. You have 2 hydrogens. You can't split it without manganese. It's not possible. So if you have low manganese, which is a trace element, we are not going to have photosynthesis working properly. Our carbon dioxide has to be split, and that is also another enzyme trace mineral reaction. We're going to create sugars of 6 carbon chain, and there are 2 groups of those, ketohexose, aldohexose. And so in the ketohexose group, you have fructose. In the aldohexose group, you have glucose. And glucose is the sugar that our cells, our mitochondria, burn as an energy source. So in a plant, I've mapped out all of the sugars. And there, in the monosaccharide group, there are 5 different groups. There are 28 different sugars. They range from 3 carbon to 7 carbon chain. And so how God builds elements, how he builds compounds, is he takes a very simple unit and he just simply sticks 2 of them together. A disaccharide is simply 2 monosaccharides placed together. In the first 12 carbon chain disaccharide group, there's a sugar called sucrose. And this is what we measure with a refractometer. It's a light refractive measurement of the sucrose sugar. And so with a Brix meter, we can look at what our Brix is telling us on the level of sucrose. There is a Brix chart that will tell you poor, average, good, and excellent. And you can look at fruits, you can look at grasses and grains, you can look at vegetables. And this is an indicator of how the plant is functioning, how it is putting components together to form nutrition. And I promise you, when you have a strawberry at 4 Brix, poor is 6, but when you have a strawberry at 4 Brix, it is absolutely not going to have any flavor, and it is not going to last very long because nature is going to tear it apart. It is not a healthy plant. It will not sustain higher life forms, and it will not produce viable seed for the next generation. So the whole process of forming nutrition can be tested. We're going to refer to this chart in a minute when we come back. Here's a wheat crop in Montana on one of my farms. On the left, we have a chlorophyll meter. It has a reading of 565.1. To the right, we have a Brix meter at 23.2. Now let's go back to the chart and let's look at what cereal grains are. Poor is 6, average is 10, good is 14, excellent is 18. This particular crop was at 23.2. So this is beyond the excellent range of measuring sucrose. The next picture is of a different field with another cereal grain. I have a Brix of 9.2 and a chlorophyll reading of 353. This, again, there's an indicator here that I don't have CO2 production, I don't have trace elements, and my sugars are not forming in high concentrations. So it's not possible to have high minerals and low sugars. They all run parallel, they all run together. And so these cofactors, these enzyme activators, are absolutely crucial. There are trace elements, and then there are our organic vitamins, our fat and water soluble vitamins. And so here we have nitrogen efficiency is directly affected by the presence of molybdenum. Molybdenum runs the nitrogenase enzyme, which converts nitrogen into various forms. So we can go from an elemental form, N2 gas, into a compound, into amino acids, into proteins. And that's the assembly line process that the companion trace elements do with these enzymes. And so manganese you can look up the mineral, you can look up the enzyme, and you can look at the function to understand what that enzyme is doing when it's activated by manganese. I've just put a couple of examples in here. Molybdenum runs the nitrate reductase and the nitrogenase enzymes that fix atmospheric gas into soluble nitrogen for legumes. Zinc runs over 300 enzymes. Coenzymes are your vitamins, vitamin B1, B2, and so on. And you can look at the coenzyme, the reaction group, the type, and then the notes of what they're doing. There is vitamin B12. So this regenerates the amino acid methionine and methane involved in the synthesis of DNA and RNA. So that's kind of important. The fact is nothing that lives without B12. You won't make B12 without cobalt. And if anybody's checked for cobalt in your soils, you have approximately, most soils that I've checked have about 1 to 2 100ths of the minimum. So it's just scarcely there. We don't put it out. We don't manage for that, but it's absolutely crucial for all of those plant functions that rely on cobalt to activate those enzymes. And so right here, we're going to talk about when you learn how to reproduce your fertility instead of buying it, your profits potential increases exponentially.